Now this question is question 10 on page 385. Looking at the question, it says liquid paraffin is a mixture of different compounds. The molecular formula of one of these compounds is C11H24. So that is the really long chain hydrocarbon that we start off with at the beginning. It tells you there, suppose that as a result of cracking experiment, a molecule of this compound gave an alkane molecule with 2 branches. So that's the first thing, an alkane fully saturated with 2 branches. Next of all, it's giving an alkene molecule, so that's double bond, with 1 branch. Lastly, we're getting another alkene molecule and there's no branches there. The most important thing when attempting this question is you're starting off with C11H24. You could draw that out if you wanted. That's 11 carbons in length, each of them all 4 single bonds, 24 hydrogens all around it. So you have a huge long molecule. Then what you're doing is coming along with a scissors, snip, breaking it up and re-changing round the carbons in order to get some of these homologous molecules. So we're not told how many carbons or how many hydrogens are involved with any of them, but we know that when you add them all up, they have to give you 11 carbons and 24 hydrogens. So this is absolutely a process of trial and error. The first one there is an alkane molecule. So the most simple alkane I could begin to draw is 2 carbons in length. So if I was to fully saturate that with all single bonds, I would have C2H6. However, the question told me I need 2 branches. If I decide to put a branch, so say for example I draw this down here, and if I decide to put a branch on carbon number 1 there, straight away what I've done is extended the longest continuous carbon chain, 1, 2, 3. So I may as well have drawn like this. It's the exact same thing. So what I've done there is made propane, which means that if you have 2 carbons in length, you cannot have branches. So the shortest alkane that I could have that will give me branches is 3 carbons in length. And I am going to take full advantage and add in 2 branches onto the middle carbon. If I fully saturate everything else, I can still see that this technically is an alkane, all single bonds. It's 3 carbons in length and it has 1, 2 branches, which is exactly what the question wanted me to do. Now, the next thing I'm going to do underneath this is write the molecular formula so I can be making sure all the time I'm not going over this quantity of carbons or hydrogens, because this is what I started off with. So I have 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens there. And if I wanted to name that molecule, you can name it from left to right or right to left, because all the activity is happening in the center of the molecule. It's completely symmetrical, so it doesn't matter. So this has a branch on carbon number 2, another branch on carbon number 2, dash dimethyl means 2 branches, propane. That's the first molecule I'm after drawing. The second molecule I have to draw here has to be of the alkene family, which means the first property is it needs to have a double bond. It also needs to have a branch. Again, if I decide to put a branch on this carbon or a branch on this carbon, essentially what I've done there is extended the carbon chain by 1 carbon in length. So that's essentially the exact same as drawing metheth propene. So it's not possible, which means that if I want to have an alkene that has a branch, it needs to be at least 3 carbons in length so that the branch can go on the central carbon and it's classified as a branch and not just another carbon in the longest continuous chain, which would give us the number of carbons in the backbone. Here I have 1, 2, 3 carbons. Each of them now needs to have hydrogens, 4 single bonds. The first carbon is already involved in the double bond, so 2 of its bonds are used up, which means I only have 2 more single bonds with hydrogen available. The second carbon has 1, 2, 3, 4 bonds already, so I can't add any hydrogens. And the last carbon is only involved in 1 bond, so I'm going to add 3 hydrogens. I've drawn an alkene. Here it is, because it has a double bond in its backbone, and I've also given it a branch. So I've satisfied all the criteria there for the second molecule. Now I'm going to add up how many carbons and hydrogens I have to make sure that these two numbers combined are not exceeding this quantity. 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens is what I've drawn there. If I was to name this molecule, on carbon number 2, I have a methyl group. This is not an alkane anymore because it has a double bond, meth, eth, prop, 3 carbons in length, and on carbon number 1, I have my double bond, so 1 ene. So that's my second molecule there. Last molecule has to be an alkene. Now, before you even get on to the last molecule, you might decide to add up these two quantities to see how many carbons and hydrogens I've left over. So 5 and 4 carbons is 9 carbons in total. 10, 11 is what I had to begin with, which means the minimum number or the maximum carbon number I could have left over is 2. 12 and 8 is 20. I had 24, which means I only have 4 carbons left over. And straight away I've drawn an alkene. There's no branches, there's no fuss. I can see C2H4 and we call that one there ethene. And that's it, okay? The most important thing is when you undergo catalytic cracking, you start off here with a long chain hydrocarbon. We know that this one was composed of 11 carbons and 24 hydrogens. This is like saying I start off with €100. I give one person half of that €100 and I give the other 2 people the other half between them. You have to figure out what's left over. So this person got €50, they got 25 and they got 25. Everyone can't get €50 because otherwise I've gone over the amount I had in the beginning. So it's really important at the end you write out the molecular formula of the 3 hydrocarbons that you've created, and the number of carbons combined must be 11. The number of hydrogens combined must be 24.